Hello, and welcome to another question from Chapter 16, the last question of the homework. So, this question deals with wave interference and is more of a question about how well you understand the properties of sine waves than a question about physics, but it's very useful in talking about acoustics and the interference of sound waves. So, a microphone situated at the origin receives signals from two loudspeakers. One is located at the x-axis at x equals 2.3 meters, and the other is on the y-axis at y equals 2.1 meters. Both speakers are adjusted so that each speaker is perceived by the microphone to have the same amplitude. The speakers are in phase with each other, i.e., they deliver the signals proportional to cosine omega t with no zero phase shift between them. With either speaker acting alone, the microphone receives the signal of A cosine omega t minus phi j, where A equals 2.5. The two phases, different phases, phi 1 and phi 2, represent different path lengths associated with a zero point 0.7 meter wavelength. Use the identity sine u plus sine v equals 2 sine u plus v over 2 times cosine u minus v over 2 to calculate the measured amplitude in both speakers are playing simultaneously. So I am just going to say that the fact that they're on different axes, the one's on the x-axis and one's on the y-axis, is just to tell you that the wave of one isn't going to run into the speaker for the other as it goes to get you through to you. So all that matters here is that y equals has a difference of 2.1 meters and x equals 2.3 meters, and that the wavelength is zero point 0.7 meters. In order to find this phase shift, what we need to do is realize that as it goes along the axis, also goes along whether the x-axis or the y-axis. Actually, yeah, the x-axis is more useful towards us. This wave is going to repeat once every wavelength. So one, two, three, and then a little bit more. So once every wavelength, the wavelength repeats, and then the phase difference between your initial omega t and your omega t minus phi is going to be dependent on how far away you are from one of these peaks. So A at zero point 0.7, 1.4 meters, and 2.1 meters, there is no phase difference. So we automatically know that for the y-axis at 2.1 meters, because it's a phase difference of exactly uh it's exactly at the wave, or it's exactly where the wave repeats, there is no phase difference. So phi 1 is equal to 0. However, phi 2 is at 2.4 meters, which is going to be about here. And you'll see that this is some distance along the wave. It's some distance along the wave. It's some angle along the wave that it's starting out at. So the way that we find the phi at this angle is noticing that phi 2 over 2 pi is going to be equal to lambda, or sorry, how far off you are from the initial wavelength or from that peak over lambda, so delta x over lambda. In this case, that is going to be equal to phi 2 over delta pi over 2 pi is going to be equal to zero point 0.2. Oh, it's 2.3 meters, not 2.4 meters, so it's going to be a little bit farther. It's going to be equal to zero point 0.2 over 0.7 which is equal to 2/7. And then multiply that by phi 2 pi, and you'll find the relationship, you'll find the angle that phi is at. Because phi is how far out you are in your angle before it starts repeating. So phi is how far out you are in your angle, and it starts repeating every 2 pi radians, whereas delta x is going to be how far you are about, how far out you are in x in like real linear space, and that's going to be repeat every lambda meters. So that relationship, those two uh, those two fractions are going to be equal to each other, those two ratios. So phi 2 over 2 pi is equal to delta x over lambda. Or phi 2 over 2 pi, in this case, is equal to 4 pi over 7, which is just bigger than pi. So it goes a little bit more than one wavelength away. So actually half a wavelength away. So actually it should be about here rather than about here. I just was freehanding what I thought was right, but it turns out it is a little bit farther than pi away. That's going to be your angle. And then when we find the magnitude total, the total value of our two equations, that is going to be equal to y1 plus y2 is equal to a cosine omega t minus 0 plus a cosine omega t minus phi 2, where phi 2 is the 4 pi over 7. By the equation that we have, sine u plus sine b equals 2 sine u plus v over 2 times cosine u minus v over 2. If we choose this to be u and this to be v, all right, instead of this, you can get this by using the fact that sine plus pi over 2 equals cosine of sine of x plus pi over 2 equals cosine of x or something like that. And just doing a lot of distributions. However, I'm going to skip to the end of that and just use the trigonometric identity that's equivalent for this, where cosine u plus cosine b equals 2 cosine u plus v over 2 times cosine u minus v over 2. So what this is going to give us is that a cosine omega t plus a cosine omega t minus phi is going to give you 2a cosine omega t plus omega t plus phi 2 over 2 times cosine um, omega t minus omega t plus phi 2 over 2, which is going to be equal to 2a cosine of phi 2 over 2 times cosine of omega t plus phi 2 over 2, which is just going to be a cosine wave times omega t that's going to go up and down. It's not going to be exactly in phase with the initial one, but it is just going to be cosine omega t. However, the amplitude is always going to be lowered from the maximum possible amplitude by this cosine omega t, or not cosine omega t, cosine phi 2 over 2. So if they were perfectly in sync, you would just have 2a times cosine omega 2 t plus uh, some phi factor, some phase factor over 2, which would just give you an amplitude of 2a. However, in this case, because they're out of sync somewhat, you're going to get that phase factor of phi 2 over 2 for your cosine, which is going to bring the amplitude to 2a cosine phi 2 over 2, which is the cosine 2a times cosine of 2 pi over 7. All right, thank you very much and have a nice weekend.